All right, gang, Math 6620, factor analysis and principal component analysis. What I want to do here is, it could get really scary. I'll just go ahead and tell you because I haven't even worked this problem. So I'm shooting from the hips, but it's a data set that I thought looked to be kind of cool. And I really don't know a lot about it, to be honest with you, but it it looked like it was something that would be applicable to factor. Well, I know it's applicable to factor analysis, or I wouldn't have gone this far. But anyway, there's something called a BIM sex role inventory, and this was a questionnaire. Now let me just get out of here and show you what the questionnaire looks like. I have it brought up on Excel. And what the respondents did, first of all, it looks like there were quite a few cases, so over 300. So that's why, number one, I was attracted to this data set, because if you remember in the data sets that we've talked about, or I'm sorry, the video that we had earlier, the number of cases above 300 is preferred. But what they did is, of the 369, well, the sample was 369 middle-class English-speaking women between the ages of 21 and 60. And what they did, they were given questions. For example, this first person, I don't know the person's age. It's irrelevant in terms of factor analysis. But there was a question about how helpful the person is. And they gave responses on a Likert scale, and the Likert scale was from 1 to 7. And the number 1 means never or almost never true of the person, where number 7 means always or almost almost always true of the person. So question number 1 feels that she is very helpful. She feels she's very reliant. Deaf Bell, I don't know what that means. She's on a 5 of 7 scale unyielding. She's extremely cheerful. She's independent. She's athletic. She is not at all shy. Over here we get assertiveness. Right here we get strippers. I don't know what. Oh gosh, I don't know what that is. Oh, strong personality. Okay, forceful, affectionate, flat. Okay, you get it right. So she doesn't think that she's very analytical. She doesn't think she's very feminine, but she is apparently a stripper. But no, I'm sorry, guys. It has a strong personality. Okay, sorry. Sometimes stuff just happens. So I haven't counted them, but I think there's, if you go across and look at the different questions, I think there's about 45 items at least, and you can look this up. I'm not making this stuff up. This BSRI is actually a sectoral inventory that exists, but the responses on these 369 middle class women. English-speaking women. This is obviously just a sample. So, but anyway, there's items that they're looking at of these helpful and reliant. And, I don't know what deaf bell, yielding and cheerful and shy and so on and so forth. 20 of these items measure femininity. 20 of these items measure masculinity. And 5 measure social desirability. Now, it would be kind of safe to say that masculinity and femininity are conceived as like dimensions of like personality. I don't know. I don't know what I'm saying here really. But I think factor analysis. I will tell you that there's drawbacks to using factor analysis here, but I think it's going to serve as a really good example to to see what happens. And the cool thing about it, I haven't done this. This is, as I do this, this will be the first time that I've ever worked with this data set. One thing I will let you know is the previous factor analysis work has been done on other data sets of the BSRI, and they have found anywhere from 3 to 5 factors underlying the items or the test questions. So, guys, we'll make it happen here and see what we can actually get. Now, I will tell you one thing. There's a lot that attracted me to this data set, but one thing that attracted me to this data set is the fact that there's missing data, and we really haven't addressed that. For example, subject number 20 on the feminine scale has a situation where that's missing data. Now, gang, there's a lot of ways you can handle this. It really just depends on what you want to do. What a lot of people will do, for example, this 366th person has missing data on the flattering question. So what a lot of people do is they'll just go ahead and run the analysis and admit we've got missing data, and there's ways that you can handle that in R. And there's also ways that people do this as well. For a large data set like this, what they will do, let me find a missing data, they will come in and replace this with the mean of the other observations. So for example, they would come down here, and I'll just go ahead and show you. I'll tell you what, I lost my place here. So part B has a missing. So what I would do is I come in here and find the average, and I find the average of all the numbers here. Well, because I think you get the hint. And the thing about it is, I think about it, he may not even give me the average because of the NA. It's going to try to add that NA in there. It's not going to work, and I think that's actually what will happen here. No, it gave me the average. So 5.92, what the researcher would do is come up here, and every place they saw a missing data, they would replace it with the mean on that. I'm not going to do that. I'm probably going to have you do something like that on a homework assignment, but I'm not going to do that here because I want to show you in R how to handle that. And guys, this is real life. This happens. This 312th person, for some reason either didn't want to answer that question, or maybe they thought they answered it. We're going to get into systematic and random error once we get into the test theory. Who knows what happened there? But the fact of the matter is as an evaluation, as an evaluator, you just simply don't have that information. Okay, all right. I'm kind of done talking. What I'd like to do now is I want to get out of this, and I want to get the data set into R. So I want to get R open and going. But I want to show you something that happens in R. Okay. Let's just say, for example, that we have something we call X, and let's say we have some numbers 1, 2, NA, and 4. Okay. Now, if I do mean of X, it's going to give me NA because it adds 1 plus 2 plus NA plus 4, tries to divide by 4, and it makes no sense. So what you can do here is you can do mean X NA dot RM equal true, and what it will do, it will treat all NAs as missing data. So what it'll do now is it'll take the other two numbers 1, 2, and 4 and add them up and get 7. Of course, 7 divided by 3 gives us 2.33. So it treats this NA.RM equal true command in in R treats it that way. Now, something we can do is you could just get new data, if you will, and do na.omit, and let's just use X. And what this is going to do is obviously it is going to eliminate the NA and just look at the new data set as 1, 2, and 4. I'm not really sure yet. Again, I'm shooting straight with you here. I'm not really sure yet what I'm going to do with this data set, but we'll think about it and get there soon enough. Okay. Now, first thing I want to do. I don't think anything I've done there so far is going to mess with anything I want to do. So let's go ahead and set the working directory. Guys, just to give you an idea of what we're going to be doing here, we're going to go through the complete analysis, factor analysis, and principal component analysis, and then I'm going to show you how to write something like this up, depending on what what we get. So, guys, let's just call this data, and so I have this in CSV format, and what did I have that as BSRI.CSV? Yeah. And you get a lot of just kind of question titles. So again, the first question, unhelpful, and so on and so forth. So you get out in, you get down at the bottom. We didn't get all the way out this far. A gentle, ambitious, competitive, love child. I don't know. Foul language. Okay, so got some stuff going on here. Okay. Now let's just kind of repeat the things that we've done before. First thing I'd want to do is look at a correlation matrix, and I get some big time problems, don't I? And my big time problems are, I have a lot of missing data. So we've got to find out, we got to determine, what we're going to do with this. For example, when I eyeball this, I see that, for example, self-sufficient, I have NAs in everything except when it correlates with itself. So again, I've got to do something with this. Now, again, you could replace all missing data with the mean. I'm not going to do that. I think what I want to do is I want to create data 1, and I want to omit all of the NAs from our original data set. So I'm creating a new data set, data 1. And now, it cleans it up, and unfortunately it's gonna restrict some things. But well, okay, I'm not really sure how it handled that. But it omitted. All right, let me check one thing. I'm supposed to have 45 variables. So if I go length of my data 1, 44. So it actually eliminated a variable. So I'd say more than likely the one it eliminated was the one that we had an issue with before. I forget which one that was. Okay, well, guys, anyway, this is something when you write up your master's thesis, you do your research, this will be something that, these types of things are the things that you explain in your methodology, chapter 3, and in your statistical results, chapter 4. So you would just say, I've used R to omit the results and the missing data, and this is what the results were. All right, gang, I feel pretty okay to go ahead and make some things happen here. So, guys, remember from here on out, we're data 1. And a point that I tried to make early on is when you have a lot of items like we do here. In the previous example, I think we only had 6 variables. And here we've got 44 after the deletion of something. And you can see that trying to examine these correlations is kind of crazy because again, there's just so much going on. So this is a situation where Bartlett's test and the determinant of the correlation matrix is really going to pay huge dividends. So, guys, remember in Bartlett's test we have to access psych, okay, and okay, I don't really know why I did that. The following object is masked from effect. Okay. So I want to run core test, Bartlett, and I want to run this on data 1. And we have a huge test statistic. We have a p-value at 0, degrees of freedom 946. If you remember the conditions to examine whether we have too many low correlations, if we have a p-value greater than 0.05, then we have problems. Clearly, we have no issues with extreme amount of low correlations. The next thing I want to do is look at the determinant of the correlation matrix. Guys, make sure we get data 1 in here. And we need the determinant to be greater than 0.0001. And it's not. So we have a problem with high correlations. With the lack of high correlations. Now, this is where it gets fun. What you would probably want to do is look at some pairwise. Just actually, take a look at correlations down each of the variables, and see if you can find correlations that seem to be specific to one particular question. Because if we can eliminate some of the low correlations, then that may address the lack of having high correlations. And guys, really, I don't see anything. Nothing's just popping off the screen at me that I would would think that we would be able to do. So when a situation like this happens, this is kind of the great thing about doing something like this on the fly, and just finding a data set where I haven't already worked out the solution stuff. This is someplace where we would just have to, when we report the results, we just have to state that we use the determinant of the correlation matrix and the threshold of 0.0001, and we have problems with insufficient numbers of high correlations. So just report to the reader. That's what we have going on. Guys, next thing, initial step we'd want to look at is normality. Normality is not an issue here. Think it through. We have Likert data. There's no reason to think that Likert data forms a normal distribution. So, that's a non-issue in this analysis. So we're not really going to be able to generalize to this BSRI to results from these 360 or so women. We're not going to be able to generalize to all women, but we're going to be able to talk specifically about our samples. So gang, let's go ahead and run our first principal component analysis. We'll call that PCA1. And if you remember from last time, we have data 1, and we need our n factors equal. Now I'm going to do length of data 1. Now, if you do length of a variable, for example, if I type length of individual, that's going to give me the number of cases for that individual. But if you do length of your data set, data 1, it's going to give you the number of variables in your data. So remember, we always want to start out with the number of factors to be equal to the number of variables that we've retained. And to keep any misunderstandings here, keep it simple, I'm going to do rotate none. Okay. Now I want to look at what I got here. Now, guys, remember a couple of things. First of all, these numbers that we get at the top are called our factor loadings, or our principal loadings, and those don't mean anything. Principal component loadings. Those things don't mean anything to us. We always want to look at our commonalities and our uniqueness, and again, those aren't going to mean much to us because we've retained all factors. We have 44 items, and we've retained all factors, so that's not interesting. But what is interesting to us to start looking at are the sum of squares loadings. Now, guys, remember, these things are our eigenvalues. And so 7.75, let's see, 18% of the variance that's explained by all 44 items is explained by this one component. As a rule of thumb, we typically want to keep the components that fall 1 or higher. But because we have such a large data set here, I'm not so sure that's a good thing to do. So let's proportion of variance. Let's look at the cumulative proportion of variance. So we're out to, I guess eventually where do we feel comfortable in stopping? It looks like to me that we're retaining what could be seen as a 12 component model here. I'm not really feeling too good about that one. Okay, well, that's the crazy thing about working on something like this on the fly. So guys, remember, when we have a sufficient sample size, we typically look at the eigenvalues that are 1 or above. There might be a pretty strong argument we retain the 12th one. So this is actually cool that this is going on, because it's going to give us opportunity to look at other things. Speaking of other things, let's come in and look at a scree plot. And I think I called that PCA1, the first one. I want to look at my values. And I want my type to be equal to lines and points. Now, when I look at my vertical, I see that going to this point, to this point, to this point, to this point, to this point doesn't change much. And when I think about my horizontal, I see the line coming through here. That didn't give me, I don't know why I put P. All right, it's more like it. Well, this is a confusing one here. So horizontal. So it looks like to me we're going to retain 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Guys, it looks like to me we need a 4-factor model, because when we go 1, 2, 3, 4, notice this is kind of a vertical move here, but I consider this to be more of a horizontal move from this one to this one. And when I come back the other way, the scree plot is extremely helpful here, much more helpful than the eigenvalues. When I come back this way, I'm horizontal, and then all of a sudden I consider that to be a vertical move. So guys, I tell you, I am looking at a 4-factor model here.